Good morning, Jean-François, Chrysalide Engineering. We're still working some electronic projects. Here is just a layout of three type of terminal enclosures from Bud Industries, and we'll try to fit different functionalities of them. The idea is that we have on the low part a resistance measurement, and we want to be able, for example, to use them as a PTC or NTC measurement through or PT100. It should also work. So all we want to be able to do is measure the resistance on various scales from the bottom terminals. And then with some logic, we can provide an output. So the O terminal should be a programmable terminal to be used as a 0.10 volts or 0.24 volts to read the, for example, analog value of the resistance measured, or to make just a threshold out of it. So we have this configuration where we have only one output, one RTD. We can have two outputs, two RTDs, and a field bus wiring. We can have an input, three outputs, a relay output, and a field bus, and three RTDs, so that we can have a little bit of logic inside. And we're going to see what sort of implementation can be done, and try to make some of the implementation on very simple circuit over here. We have a boost power supply. This microchip circuit was chosen because of the low price and the efficiency of it and the high voltage. It's supposed to work up to 48 volts if we take the datasheet of this circuit. I tend to use Texas Instruments and microchip datasheets. There are a couple others manufacturers that do very good work of documenting. So something I love about this datasheet, we can already see that they have documented everything. Even though these kind of pins are very standard, they say that the enable pin logic should be put low and should not be kept floating, which we have done over here. So we put the enable pin on jumper over here. So the enable goes through pull up to input voltage, and with the jumper can be grounded. So we will have like two terminals to be able to put the device in off. PG is a power good output pin, and it works with 93% of the output voltage and 90%, so 3% of hysteresis. Below 90% we get the power good going lower. We have the power good with the label PG. We didn't make anything out of the label PG, and we really want to wire this one into this circuit over here. Here we have the schematic of this slightly different project, and we will put this provisionally on any of the pin over here. Let's put it on pin 0. So this will be our power good, and what we want to make is if the power gets off, take some actions before the battery will be empty, provisionally. So, and we have our feedback. We have set for 6 volts over here, and that's just a buck converter. But what we have done is calculate the tolerances out of this circuit and put everything in this text block over here. So this circuit, provided we have 1% tolerance on the R11, R12, we should be 2% tolerance on the MCP circuit, and the complete tolerance should be 4%. So we should get 576 to 624 volts. So we just take the 2 minutes it takes to calculate this value and put them in a text block over here, very neat. So that when we'll start to do some testing, we can actually make sure everything is fit. And we use a 6 volt output. We have the boost diode that should be connected to 3 volt and 5.5 volts. So the circuit is still correct because we have a 6 volt output over here and a 5 volt behind this regulator over here, because this will have some influence from the line supply to the output, and as well rate voltage depending on the load and depending on the. So we want to make some analog usage of the analog pins in this microcontroller, and therefore we want to have this from this 6 volts we'll make 5 volts, and this is a LDO with about 0.3 to 0.4 volt loss. So with just 6 volt input and 5 volt output, we should have very well regulated output. And we see that we have an RC filter with 10 kilohertz over here. So we want to make an additional filtering to supply an analog VCC back to this microcontroller. And in this microcontroller, we also provisionally have the battery, voltage for real-time clock, the 32K low frequency crystal for RTC, and the 16 meg for high frequency to supply to the PLL and to the main clock of the microcontroller. We can also repeat that we have a 6 volts output over here. Something like this is just making the circuit easier to read. If you didn't know, we need to use the power flags over here and over here, because these pins, they like to have a power flag attached to the particular rail at any point of the circuit to be sure that it was identified as power supply. We have that here. We don't have any test point. We need to add them. We have 8 volts input because we want to have a 2 volts margin from 8 to 6 volts output. Based on this circuit, it's the lowest limits, and the upper has been set to 30 volt, but we can go higher, except that we have a high voltage protection over here set for 40 volts. And again, if we check, it can go up to 48 volt transient. This circuit can go to 48 volts, and this diode is a 40 volts switch off to switch on, and then about 46 volts at 6 amps or something like this. We have this protection diode. If we check the type code, we use the 40. The 40V is a standoff voltage of 40 volts basically, which means negligible current up to this voltage. But then when it starts conducting, it's rising up to 44 and 47 volts, and we have even a clamp at 64 volts. So I think this diode selection is not correct anyway, because if we want to protect properly the chip, we need to probably get down to this particular diode type code, because we want to stay far under 48 volts with 8 amps, which is if we have any transient voltage, then we want to be conducting and protecting well under 48 volts. So this is really the maximum voltage we can use, 30 volts. So we'll change it right now. This diode type code needs to be this one. And then what will happen is that we have 3 amp fuse, so we want this diode to be conducting. And say if 36 volt input, then we will blow the fuse. That's good. And then I'll add that we have a max operation 30 volts, max protection 48 volts, thereabout. 48 volt, 8 amps. So we see that this should be working fine, as long as we have some over voltage between 30 and 48 volts. First of all, the output stage will be protected, and the fuse will finish by blowing up if the transients are in the region of the millisecond or something.